Alright, so last week we introduced the pH scale. We just talked about what it meant to be acidic or basic on that scale. Alright, so if you use like a pH test strip and you saw a high number or a low number, did you have an acidic or basic solution? Or where was the middle, right? Like what did it mean to be in the middle? Okay, so that's what we did, and we had something like, alright, so there's 7 and that's neutral. Which is weird. What scale puts 7 in the middle, right? Like, why is that? And if it gets higher, to a higher number, that means it's becoming basic. And if it goes to a lower number, it's becoming acidic. Okay? That's what we talked about last week. That's it. Just the number system and so on and so forth. Okay, so it's an exponential scale, and we're going to talk about why 7 is neutral. Why not 5, right? That's a pretty standard middle number. Most things go from 0 to 10. Well, it turns out, by the way, that this can go to 0, it can go negative, it can be negative 1, negative 2, so on and so forth, and it can go, in theory, infinitely high, although you can only get so much OH minus into a solution in reality. At a certain point, solubility rules come into play with those strong bases, right? At a certain point, it's a saturated sodium hydroxide solution. So, let's just jump into it, alright? So mathematically, that's what we're doing here. We're doing the math. Here's our formula. So it's an exponential scale, so pH is going to equal the negative log of our concentration of H+. And this is log base 10, by the way. So you just find that log base 10 button on your calculator, and this stuff's not too bad. Alright, you don't have to do this in your head. You don't have to pull out an old school logarithm table and look up the values. Just use your calculator. Just punch it out. And you want to find that log base 10 button, and you want to get comfortable doing these calculations on it, because these are actually going to be pretty vital. So, what are we talking about here? Well, for example, if we have a solution with concentration of H+, remember those square brackets mean concentration, is equal to 0.01. And there's an implied molarity there. We don't always write it after the square bracket. If you see this, it means concentration of H+ in molarity, and it's 0.01. Alright, so this is an acidic solution. Maybe, we'll find out, actually. Maybe it's basic, I don't know. You don't know how this relates to pH scale yet too well. I got ahead of myself, I read the wrong line in my notes. And so how do you get something like this, by the way? It could be an HCl, a 0.01 molar HCl solution. It could be something like that. A strong acid, alright, is going to have the molarity of H pluses that come off of it equal to the concentration of H pluses, right? So for every HCl I put in, I get an H plus. So if this was an HCl solution, it was 0.01 molar, then my H plus concentration would be 0.01 molar. Just be aware of that. Weak acids is a lot trickier, so you can't really work with those right now for concentration of H plus and pH and all that. Alright, so what is the pH of this solution? That's where we're going here. Alright, well, our pH is going to equal the negative log of our concentration of H+, which is 0.01. Okay, and so if you punch that up in a calculator, you do log base 10 of 0.01, and then you multiply by -1, you should get, and you want to test this out in your calculator, make sure you get comfortable doing this and getting a 2. That is a pH of 2. And so this is an acidic solution. Now we can confirm, right? It's got a pH of less than 7. It's acidic. It's bordering on strongly acidic, but it's acidic. Okay, so what about neutral water? Like, why is 7 neutral? Well, in neutral water, or pure water, our concentration of H+, we talked about this in the last video, is 10 to the -7. So what's the pH of that going to be? Well, It's going to be the negative log base 10 of 10 to the minus 7. And I'll make a note up here as well. So remember, this is log base 10. You got to be careful because there's also log base e. Both of them are used, unfortunately, very interchangeably in this notation. Shortcuts sometimes crash into each other. Alright, so negative log of 10 to the negative 7. Alright, so if you punch this up in your calculator, you should get a 7. Alright, so make sure you're getting good at that. And I'll give you plenty of opportunity to practice on the practice sheet. It's only 2 calculations we're doing here. This is the first one. Okay, so, well, if neutral water has a pH of 7, well, guess what that means? That means a pH of 7 is neutral. So that's where it comes from. It just comes from nature. Nature's a jerk. It should have been 5. It should have been 5. That would fit very nicely with our social conventions of where the middle of a scale is, or 50, right? Somewhere, something like that, or even a 10, a scale of 0 to 20, or whatever. But it ends up being a 7. So that's where the pH of 7 being neutral comes from. It just comes from the fact that water, pure water, is going to have some H plus in it. Not a lot, but when we plug it into our pH calculation, it comes out to be a 7. Alright, well, what if we want to go the opposite way, right? So this is our magic formula to calculate pH if we know H plus, but quite often what we do with a solution, maybe you've done this with a swimming pool or something like that, you test the pH. Well, what's the H plus concentration if you know the pH? So the pH is often what's directly measured, not H plus concentration. So titrations will get you H plus concentration. I've never known someone to do a titration of pool water. That's a lot of work. But what you can do is a pH measurement very quickly using an indicator solution or something like that. And then you do the little comparison. They have the little reference chart, and you got your little dropper over here, or a test strip. I prefer the test strips myself because I'm a lazy chemist, and I understand that litmus paper would not ever betray me. But anyway, so what if we want to go the opposite way? So we talked about H plus concentration to pH, but what if we measure pH? Well, it turns out that there is a way to reverse a logarithm mathematically. So, the opposite of addition is subtraction. The opposite of multiplication is division. The opposite of a logarithm, maybe you know this, maybe you don't, it's not as common as those other pairings. If you do, think about it, try to figure out what it is. If you don't, I'll tell you. It's an exponent. Okay, so logarithms and exponents are opposite of each other. So how do you reverse an exponent? Use a logarithm. How do you reverse a logarithm? Use an exponent. So that means that concentration of H plus is equal to 10 to the minus pH. Right? All that build, and it's just that. Okay, so this is 10 to the power of the pH, not 10 times pH, and it's negative, by the way. So for example, you have a solution with a pH of 10, which my pool wasn't far from when I moved in because the previous owner did not manage pH. So, which by the way, that's really bad. You want it a little over 7. It's been fun. I've gotten to do a lot of pool chemistry lately. So that's why when I'm talking about pH, I keep giving the pool as an example, because I'm literally going out there and testing the pH every day and adjusting it. You got to bring it down slowly. There's a lot of different other processes. Maybe I'll talk about it when we get to equilibrium, because there's a lot of equilibrium processes in play. So you've got a solution with a pH of 10. Maybe it's my swimming pool, 4 weeks ago. But what's the H plus concentration for that? Well, H plus is going to be equal to 10 to the minus 10. Good enough for me. Boom. Done. I'm not going to write 0.00 blah 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 1. Okay? That's I got better things to do with my time. So I'm going to keep in the exponential form. That's it. You don't even need to find the button on your calculator. Now, if you had something more complicated, you'll want to use, there's usually a 10 to the x button on your calculator. And so if we have something like a pH is equal to, 4.7, well then concentration of H plus is equal to 10 to the minus 4.7. And you might not always have that option available. And so you want to punch it up in your calculator and then get whatever value that is. So that's going to be, I'm just going off the cuff here, so I actually have to calculate it, so bear with me. So we got 10 to the minus 4.7. Alright, and according to Lay Google, it's about 2 times 10 to the minus, we got 1, 2, 3, 4, 5. Which makes sense. So it's a little bit more than 10 to the minus 5 and a little bit less than 10 to the minus 4. Alright, so, it's below 1 times 10 to the minus 4. So it's just an estimation tool. But it's above 1 times 10 to the minus 5. It's about double this and, much smaller than that. So 10 to the minus 4 would be here, 10 to the minus 5 would be here. It's in the middle. Alright, so that's our answer. So it's above this and below that. So that's a reasonable answer. That's how we can kind of check it. So, the last thing to mention here, and again, just use your calculator button for that. The last thing to mention here, something to note. It's a logarithmic / exponential scale. So doubling our H plus concentration is not going to be doubling pH or even halving it. It's not going to do either of those. Alright, so for example, let's compare two solutions. Let's say we have a concentration of H plus equal to 0.1 and a concentration of H plus equal to 0.2. So I double my concentration of acidic protons in the solution, H pluses. Well, what are these pHs going to be, right? So if I double H plus, I'm telling you it's not going to double, but I'm going to prove it. Alright, we're going to do the calculation. We're going to see this ourselves. The pH is going to equal negative log of 0.1, which if you punch that up in your calculator, you should get a 1. Or maybe you're good enough with logarithms, so you can just see that. So, if it's just a power of 10, like this is 10 to the minus 1, I can do that in my head. And if you know your logarithms well, you can too. When it's something like this, if you're really sharp on them, you can estimate. I'm not right now, so I punched it up in the calculator. And I get about 0.7. So it only went down 30%. Okay, I doubled the concentration and I dropped 30%. So it's not 1 to 1 because this is exponential scale. And so if I look at it on a graph, if my concentration of H plus goes like this, well then my pH is going to change like that. It's going to have curvature. Okay, so what happens is that it turns out that most things, like chemical reaction rates, stuff like that, are going to need exponential growth in concentration, and that's going to get you a straight line to something like pH, something exponential. But we'll deal with that later. For now, I went a little bit above and beyond here. So for now, just be able to do a pH calculation, a concentration of H plus concentration, be able to perform that with your calculator, and just remember that because it's not like a multiplicative scale, it's a logarithmic scale, that if we double one, that does not equal doubling the other. And vice versa too. If I double pH, I'm not doubling H plus concentration. It's going to be something far more exponential than that. Alright, so we'll leave it here. Hopefully now you're able to calculate pHs and whatnot, or at least have the understanding to be able to get into practicing that. And we're actually going to step out of H plus and these kind of water-based processes and acid bases, and we're going to talk about electrolytes. So we're going to talk about conductivity of water solutions, alright, aqueous solutions. And then we'll have a few more videos after that this week to work through as well.